So here we have an example of an integrated rate law problem. So we have this reaction. Some reactant gives products, gives a straight line plot of 1 over A versus T with a slope of, that should be positive. Positive slope. Assuming that A naught is 0.01, calculate the time in seconds required for the reaction to reach 23% completion. So we've plotted 1 over A naught, or 1 over A, I should say, and we plotted time. We get a linear trend. And so here the slope equals K. So when you plot 1 over A versus T and you get a linear trend, the slope equals K. This is for a second order reaction. Remember, for ln of A versus T, it's first order, and for A versus T, it's zero order. So here we want to use, it's a second order reaction. That means the slope equals K. So K is 0.00735. We have our initial concentration. We want to calculate how long it will take until the reaction reaches 23% completion. So here it says 23% completion. That means 23% of the reactants got converted into products. So that means the final concentration of reactants is 77%. So at A naught, let's say we have 100% at A of time T. And here we want to know how long it takes for 23% completion. That means 23% of the reactants get converted into products, which means we have 77% of the reactants left. But for second order reaction and zero order reaction, we can't use percents. We actually have to use concentrations. So 100% is 0.01 molar, which is given to us in the problem, and 77% is whatever 77% of 0.01 is. And we get 0.0077. So for zero and second order, you can't use the percents. You have to actually use concentration. So now we have the concentration at A naught and at time T. Again, the slope equals the K, so we know what K is. And since it doesn't give us units of K, we'll just assume that the unit includes seconds. So remember, second order is molarity per second. So now we have K, we have our initial concentration or final concentration. The equation is 1 over AT equals KT plus 1 over A naught. So here we're solving for K. So I'm going to do 1 over . So now I'm going to plug in my numbers. And do make sure you use parentheses in your calculator, because if you don't, it does it based on orders of operation. And depending on how you put it in your calculator, you may get some wild answer. So now we'll simplify. and we get now we can solve for T. And we get about 4,064 seconds. So that's how long it will take to reach a concentration that is 77% of reactants is left, aka 23% completion. So when talking about reactions, why reactions happen the way they do, we have to talk about one type of theory, which is collision theory. So the fundamental basis of collision theory is when molecules collide, they react. Or this could be atoms or ions. But when for anything to occur, for a reaction to occur, particles have to collide. And so that's what collision theory says is particles have to collide in order to react. But there's a few intricacies we have to learn about as well. It's not just that any molecule collides, it reacts. The molecules have to have the correct orientation. So when the molecules, I use molecules, but also for atoms and ions, when molecules collide, they have to be oriented the correct way so that when they collide, they react. So it can't just be any type of orientation. It has to be a particular orientation. And secondly, they have to have sufficient amount of energy so that when they collide with the correct orientation, the reaction can occur. So you need collisions, orientation, and energy for reactions to occur. So why are concentrations multiplied in the rate law? Because here, if we have two molecules of A, each A reacts with each B. So that's a total of 4 collisions. So 2 times 2 gives us 4. Now if we have 3 molecules of A reacting with 2 molecules of B, we have a total of 6 collisions. 3 times 2. So every molecule reacts with every other molecule. And then likewise, if we have 3 A's and 3 B's, 3 times 3, we have a total of 9 collisions. And so the more molecules we have, the more collisions take place. Now, one term we use in collision frequency or in collision theory is collision frequency, and it's a number of collisions in a given unit of time. And so this has kind of a limit on how fast reactions can take place. So for example, here we have a chlorine radical reacts with NaCl. So again, this NaCl molecule has to be oriented the correct way. And so when the chlorine reacts with the chlorine radical, we have a collision, and you see we form Cl2, and we form NO. And again, this is starting with a chloride or a chlorine radical and NaCl. So if the chlorine is oriented, when it strikes the chlorine radical, we form these products. 1 molecule of Cl2, 1 molecule of NO. Now, if the orientation is different, let's say we rotate it 180 degrees, and now the oxygen reacts with the chlorine radical, then you see that we don't get any reaction. So the chlorine radical is still in place, and NaCl is still intact. So it has to have the right orientation for a reaction to occur. So if we have the chlorine atom on NaCl strikes the chlorine radical, reaction occurs, we get Cl2 and NO. But if we rotate the molecule 180 degrees, and let's say now the oxygen strikes the chlorine radical, no reaction occurs because it wasn't the right orientation for the reaction to occur. So you have to imagine in the chemical reaction, you're going to have millions and millions of collisions. Not all of those collisions lead to reactions. Only the ones with correct orientation and the correct amount of energy. Because there's a certain minimum amount of energy you need when molecules collide so that they react. And so one way you can affect the rate of reaction and the rate constant is by temperature. So if you change the temperature, you can change you increase the rate constant, which increases the rate. So here we have 4 experiments involving an ester and water. You see as the temperature increases and we have the same concentration of reactants, the rate increases as well. And also the rate constant increases too. And so the reason this is because remember there are 3 things you need for a reaction: collisions, orientation, and energy. So as you increase the temperature, you're kind of giving those molecules a head start so that when they collide, they have the right amount of energy. So that's why as you increase temperature, the rate increases because now more molecules are colliding with the correct amount of energy to form a reaction. And here, as you can see, the rate constant increases exponentially with T. So as you increase the temperature more, your rate constant goes up because now you have more reactions with sufficient energy. So it's kind of like if someone's running a 100-meter dash, and instead of starting at 0 mark, they start at 10-meter dash. Well, they're going to finish faster than those that start at the 0 mark. It's kind of the same thing with temperature and reactions. The higher the temperature, the molecules have a faster moving start, so when they collide, they react. And this is the equation that we can use to calculate rate constant, the Arrhenius equation. So rate is equal to, or rate constant is equal to some coefficient A, e raised to the negative EA over RT. And so the higher the temperature, the larger the K, because if you notice, it increases the rate faster. So what happens is you increase T, this exponent becomes smaller. So a smaller negative means it's going to be not as negative as if it was a larger negative exponent. So e raised to a smaller negative exponent is going to be more positive than e raised to a larger negative exponent. So as temperature increases, this factor here, EA over RT, becomes smaller. And so we're going to talk about next, what is this EA, which is called activation energy. And that's the energy component of collision theory. So again, we have collisions need orientation and the correct amount of energy to react. And activation energy is the minimum amount of energy needed for a reaction to occur. So, and activation energy, again, is the energy that we're talking about for reactions to occur. And like we saw on the previous slide, temperature does affect rates, and it also affects the ability of molecules to overcome the activation energy as well. And so activation energy is the minimum energy for a reaction to occur. So molecules have to have this minimum energy that when they collide, they react. And what happens is when they react, they form what's called an activated state. And so when we're talking about activation energy and reactions, we usually use what's called a energy diagram. We'll talk more about this in a little bit, but this is referred to as an energy diagram. And on the left side, you have reactants. And on the right side are products. And so in the middle, this hump we have to overcome is the activation energy. So once you overcome this barrier, then the reactants form products and it tumbles down to the product state. So this is usually referred to, as we'll see in a little bit, the transition state is at the peak. So it's like a transition from reactants to products. One thing to also note is if the products are lower in energy than the reactants, this would be exothermic, meaning it's releasing energy as you form products. If the products were higher than the reactants, that would indicate that it's endothermic. And the difference between the activation energy of the forward and reverse reactions gives you delta H. So if we look here, if we take the energy difference right here, this is referred to as, this is one way to find delta H. It's the difference between the activation energy of the forward reaction over here on the right and the activation energy of the reverse reaction. So the difference between the two will give you delta H. So it's E of A forward minus E of A reverse. And since the reverse is greater than the forward, delta H would be negative. So again, when products are lower than reactants in an energy diagram, it's exothermic. When the products are higher than the reactants, it's endothermic. That means delta H is positive when it's endo and negative when it's exo. And that's the equation, like I mentioned earlier, forward minus reverse gives you delta H. So as we mentioned, temperature does play a role in the collision energy. And so there are two things with collision: the frequency, so how often they collide, and then the collision energy, the energy that when they collide, they have the right amount of energy. And so a rise in temperature means that particles move faster, they collide more often. However, as we'll see on a table in just a second, this is just temperature only plays a minor factor in this. The major thing temperature does is with the collision energy, it helps the molecules obtain enough energy so that when they react, they form product. So that whenever you increase the temperature of a reaction, you're going to increase the number of molecules that when they collide, they form a product. To kind of give you a simple analogy to this is if you take, a piece of fruit, usually you stick it in the refrigerator, it takes a very long time for that fruit to spoil because you're decreasing the temperature of the reaction that causes the spoilage of the fruit. But if you take that piece of fruit out, maybe put it in a very hot area, over time you see that the spoilage of the fruit happens faster because the heat helps increase the spoilage of the fruit. Similar with reactions. Reactions happen, they collide, they react, but if you add more energy, now when they collide, they have enough energy so that they will react to form products. And so in this graph in the lower left-hand corner, you have two curves. You have the blue curve, which is at temperature T1, and you have the red curve, which is a temperature greater than the temperature at T1. And you see now we have more collisions that form reactions. because now they have more sufficient energy to overcome activation energy, which is shown right here. So as you increase temperature, now you have more collisions that lead to reactions. And so here we're showing you about activation energy and temperature. So as you increase activation energy, you see a decrease in the collision frequency. So again, we're at a constant temperature. We increase the activation energy of our reaction. We see a decrease in the number of collisions. Now, if we increase the temperature but keep activation energy constant, we see that as we increase temperature, we increase the number of successful collisions. And so here it goes to show you that if you increase activation energy at a constant temperature, you decrease the number of successful collisions that the molecules have, because now you need more energy to overcome that energy barrier. So it's going to take those molecules that are moving very fast to collide and react with the right amount of energy. But if we keep activation energy constant and then increase temperature, you see that now we have an increase in the number of successful collisions that can occur, because you're giving those molecules a head start to overcome the energy barrier. So as we increase temperature, we see more successful collisions, means the rate increases, so we form more product. Now, how do we calculate activation energy? Well, we notice the Arrhenius equation that we showed earlier. Now, we don't use this form in particular. We'll see that we use a slightly different form of this. What we do is we take the ln of both sides and we get this equation here. Ln of K equals ln of A minus EA over R times 1 over T. So what we did is we took the ln of both sides, and then once we do that, we can get rid of the E and we get this form of Arrhenius equation. So this is a very similar to a linear curve, y equals b plus mx. And so what you can do is if you plot ln of K versus 1 over T in Kelvin, the slope equals negative EA over R. So again, you plot ln of K versus 1 over T, and temperature in this has to be in Kelvin. Then the slope you get is equal to negative EA over R. And R here is the 8.314 gas constant. So if we know R and we know the slope, we can calculate the activation energy. And the activation energy is always going to be a positive number. So if your activation energy is not positive, you've done something wrong. So again, you plot ln of K versus 1 over T in Kelvin. The slope you get is equal to the negative of the activation energy divided by R. And R is a constant 8.314. So this is one way you can determine the activation energy of a chemical reaction. You measure the rate constant at different temperatures, you plot that, you find the slope, and you can determine activation energy. Again, activation energy is always a positive number. Now, if you just have 2 points and you want to find activation energy, you can use the bottom equation, which is ln of K2 over K1 equals EA over R times 1 over T1 minus 1 over T2. So if you know your rate constants at both temperatures, you can plug them in and solve for activation energy. Likewise, if you know your activation energy and you want to change the temperature, you can calculate the new rate constant. Now, in these types of problems, it's very important that you remember your algebra, because a lot of errors occur when algebra mistakes happen. So you want to make sure that you don't make those simple algebra mistakes, because that'll cause your answer to be incorrect. So this is a form of Arrhenius equation we use when we just have 2 points. If you have a graph, then you plot ln of k for 1 over t, you can find the activation energy that way. So we looked at collisions, we looked at activation energy. We said that molecules need to have the right orientation to collide, and that's what we're going to be looking at here, is how the molecular structure affects the rate. And so again, with collisions, as we said before, we need effective collisions, so collisions that lead to products, so they have to have the right orientation and the right amount of energy. And so if we look here at the right-hand side of the screen, we see NO and NO3 reacting. So there are many different ways you can orient the molecules for the reaction to occur. So one way is if the oxygen on NO reacts with an oxygen on NO3, no reaction occurs because that's not the correct orientation. Now if the oxygen on NO reacts with the nitrogen on NO3, so this is NO, and NO3, no reaction occurs. Now if the two nitrogen atoms collide, so the nitrogen on NO and the nitrogen on NO3, no reaction occurs. And then if the nitrogen on NO reacts with another oxygen, we see no reaction occurs. And it's the way the oxygen and the nitrogen are oriented. So you see this NO is 90 degrees to the O. So no reaction occurs. But now if we orient the nitrogen on the NO at such an angle where it's almost linear with the oxygen, we get an effective collision, and then we have a reaction. So out of 5 different orientations, only one of them leads to an effective collision. When they have the right angles, when they collide, they form a reaction. So imagine 1 out of 5 collisions leads to for example, to a formation of products. And so the molecular orientation is built in that term A in the Arrhenius equation. And so A is made up of 2 components, which is P, the probability factor, and Z, the collision frequency. Now we're not going to do any calculations involving this form of Arrhenius equation. We're mainly going to be doing ones involving the one on the previous slide. Oopsie doopsie. So another theory we're going to talk about is transition state theory, which is what occurs when we're overcoming that activation energy. And this is what we will call in a little bit a reaction. It's something that occurs for a very short period of time. It's a very high energy species that exists just for a particular moment when you have these effective collisions. So it's kind of like the midway point between reactants and products. And so we refer to this as a transition state or activated complex. And this only exists at the activation energy. And it only exists for a short time, because then you go from reactants down to products. So for example, here we have a reaction involving bromomethane plus hydroxide gives us bromide and methanol. So we have one molecule of bromomethane reacts with hydroxide, gives us bromide and methanol. We want to look to see what would be the transition state of this reaction. And so what happens is the transition state involves the formation of a carbon-oxygen bond and the breaking of a carbon-bromine bond. So here, let me draw this, and we'll look at it more in depth in just a second, just to show you. So our reactants and our products are this. Now at the transition state, this occurs. So what's happening is this bond here is getting longer, and this bond, the carbon-oxygen bond, is starting to form. And eventually what will happen when we form products is the carbon-bromine bond will break and the carbon-oxygen bond will form. So when you reach the transition state, again, the carbon-bromine bond has been elongated and the carbon-oxygen bond is starting to form between the two. And then once you overcome this activation energy, then the carbon-oxygen bond forms and the carbon-bromine bond breaks. And that's where you get your products, Br- and CH3OH. So to look at this a little bit more in depth is this energy diagram. So again, this is our initial starting point, which is right here. We have our reactants. You see that there's electron density between the carbon-bromine bond. There's no electron density between carbon and oxygen. As the reaction starts to occur, before we get to the transition state, the electron density between carbon and bromine starts to decrease, and the electron density between carbon and oxygen starts to increase. When we get to the transition state, now we start seeing a bond start to form between carbon and oxygen, and bromine starts to move away from the carbon. After we get past the transition state, you start seeing the formation of a single bond between carbon and oxygen, and bromine starts to move away from the carbon. So there's no electron density, or very little electron density left between carbon and bromine. And then at the final state, bromine or bromide is completely separated from the carbon. There's no electron density here, and you have your CO single bond between carbon and oxygen. So if you notice on the dashes, before the transition state, bromine is only a little bit away from carbon, and OH is very far from carbon. When we get to the transition state, they're about equal lengths away from the carbon. After transition state, the OH comes in closer, the bromine goes further out. When it gets close enough, the hydroxide forms a bond with carbon and bromine breaks apart. And so this is what it is occurring as reactants before the transition state, and then after the transition state to form products.